When you first learn calculus, you are trapped on a single line. But the moment you add a second variable, that rigid path stretches outward into a vast, undulating landscape. Adding a second variable transforms the mathematical domain into a two-dimensional surface. This shift changes the underlying geometry, requiring us to reevaluate how we measure behavior at any single point. Think about the baseline we already know, a one-dimensional mapping. A simple function like y equals f of x takes an input from one flat number line and maps it to a specific output on another line. Look at this sketch. For z equals f of xy, we leave the number line behind. We are now mapping an entire two-dimensional coordinate plane to a real number line, resulting in a three-dimensional surface. Because our geometry has expanded, our foundational axioms, limits, differentiability, and approximations must scale with it. They can no longer operate on a strict left-to-right track. They must adapt to a space with infinite directions. On a single variable line, finding a limit is highly constrained. Within a linear interval, you can only approach a target point from two directions, the left or the right. In two-dimensional space, the neighborhood of approach changes. As shown in these notes, it transforms from a linear segment into a circular disk, defined by a specific radius. In this one-dimensional example, the formal epsilon-delta definition maps a tiny domain interval to a tiny range. We lock in a tolerance, epsilon, and solve for a precise distance, delta, that guarantees our output stays within that bound. But for two variables, the math becomes stricter. As highlighted in this section, a multivariable limit must be path-independent. Your outputs must stay within that epsilon tolerance, regardless of the angle you use to cross that circular delta neighborhood. This introduces a critical vulnerability. With an infinite number of paths approaching the center of that disk, if even one trajectory yields a different height on the surface, the limit does not exist. This is why these notes outline the two-path test. We define two trajectories. If they produce different values, the limit fails. Here, evaluations along the line y equals mx depend entirely on m. Because the output changes based on slope, the limit is invalid. Testing linear paths is insufficient. A multivariable limit exists only if it survives every possible geometric approach across the entire domain. Once continuity is established, we analyze rates of change. In two dimensions, slope is directional. To find it, we must lock one variable constant, effectively slicing the 3D surface with a vertical plane. These are our partial derivatives. By keeping y constant, we calculate the exact rate of change of the surface with respect to x along that specific slice. Read this top note carefully. The mere existence of partial derivatives does not guarantee that a function is differentiable or even continuous. True differentiability requires more than isolated cross-sections. It requires a unique, continuous tangent plane. Imagine a flat, rigid pane of glass descending to balance perfectly on a single point atop the surface. Here is the exact equation for that plane. We construct it by combining our x-slope and y-slope, forming a linear grid that approximates the surface at that specific coordinate. The tangent plane is the two-dimensional equivalent of a tangent line. Its existence proves the surface is smooth in every direction simultaneously. Because a tangent plane is only accurate very close to a single point, we use Taylor's theorem to approximate the wider shape of complex surfaces using polynomial curves. Looking at this 1D graph and formula, the single variable logic is clear. We use higher-order derivatives to bend a tangent line until it matches the curvature of the function. To approximate a surface, we have to scale this logic, accounting for curvature across multiple axes at once. Look at this boxed general expansion equation for two variables. We are now using combinatorial operators. Every term in the expansion must account for simultaneous increments in both x and y. Mixed partial derivatives, such as f sub xy, quantify how the x-slope varies as the y-coordinate shifts. They allow us to capture the twisting or saddle-like motions that define a complex surface. Summing these terms creates a quadratic paraboloid. Geometrically, it's like taking a wireframe bowl and letting it morph to wrap tightly over an irregular landscape. While the math becomes combinatorial, the goal remains to locally tame complexity through systematic approximation. We have traced the evolution from lines to surfaces, intervals to disks, and tangent lines to tangent planes. When we see these multivariable tools operating together on a complex landscape, we can navigate the topography of data with the same rigor we used for a simple number line. Although the math is more rigorous, the fundamental philosophy of calculus survives the dimensional transition. These models provide the precise tools needed to map physics in a jet engine or handle optimization in a neural network. Treating every added variable as an additional degree of geometric freedom provides the precision needed to model and predict the behavior of complex systems.